Okay, let's start with what we are building. In this project, we are building an efficient low power wake word detection system specifically designed for microcontrollers. The idea is to have a system that can continuously listen for predefined keywords such as yes or no and then triggers the correspondingly response when that word is detected. There are the key features: real time audio processing in this system designed to capture and analyze the audio instantly. Instead of storing long recordings, it works with very short audio windows, usually 1 seconds or less, and the processing on the fly. Next, machine learning based clarification. Once the audio is captured, a lightweight neural network classifies the spoken word. This allows the system to actual wake word from background noises and silence or other words. Next, minimal false activation. One of the biggest challenges in the wake word detection is preventing accidental triggers. To achieve this, the model is trained on large and diverse datasets, and the recognition algorithms apply smoothing and thresholding to make sure activations are intentional. Next, efficient hardware implementation. Since we are working with microcontrollers like Arduino Nano 33 BLE sensors on the SparkFun Edge, resources are extremely limited, both in terms of memory and CPU. That means model must be small and optimized to run efficiently without draining the power. Okay, next we'll see about application architecture. In this, we see the application architecture of our wake word detection system. In the heart of system is model inference, where a TensorFlow Lite models run directly on the microcontroller. The system performs real-time processing, continuously listening to audio and converting into a features for classifications. Since we are working with limited hardware, the design focuses on low power consumption. It will be making it practical for battery based devices. Where the wake word is recognized, the system performance even triggering, for example, tuning on device or activating a speaker. More advanced design can even support self-learning, allowing the systems to adapt to a new words or different voices through retraining. Okay, next we will see about introduction model. In the slide, introduce the wake word detection model, which is small convolutional neural network or CNN, designed specially for low power microcontrollers. The goal is to classify short audio clips into categories such as yes, no, unknown, or silence. The model has few important features. Its processing input as spectrogram, which are visual representations of sounds showing how frequency changes over time. This makes speech patterns easier to classify. The network is lightweight and efficient. So inference runs with very low latency even on device with limited memory. Another key feature is that model can be fine tuned with new data, improving accuracy and reducing false positive. And finally, it support which compresses the model so it takes up less memory and requires fewer computations. If your figures show the CNN architectures, you can explain the input spectrogram passes through conventional layers, polling, and finally a fully connected output layers that predicts the spoken words. Okay, let's see the all the moving parts. To build a complete word detection system, one of the first key components we need a Arduino provider. Its role is to capture and pre-process raw audio input from the microphone It supports different microphones, configurations, and sampling rates, making it adaptable across device. In the practice, it also applies basic pre-processing such as reducing backgrounds, noise, and improving speech clarity so the signal is cleaner before reaching the model. The next stage is future provider, which takes the audio and converts into a spectrogram using a fast Fourier transform or FFT. From this spectrogram, the system extracts key frequency features that represent the spoken words. This real-time features extraction ensure the system remains responsive and can quickly decide if a wake word was spoken. In the figure, you can see the processing pipeline. On the left, we start with the raw waveform captured by the microphone. This looks like a series of up and down signals in the time domain. The next step is applying a FFT to break down this waveform into a frequency components. Finally, the right we will see the spectrogram image which shows how the frequencies change over time. Darker or brighter regions indicates stronger frequency energies. This spectrogram it's what we feed into the neural network for classifications. And the TensorFlow Lite, the next stage of the system, which is responsible for running the trained wake word detection model on the microcontroller. It processes the incoming spectrogram data and classifies the audio into the categories such as yes, no, unknown, or silence because it's the optimized for embedded device that inference is both fast and power efficient. Once the model output is probabilities that can come and recognize the steps in, its role is to analyze these outputs and decide whether a valid wake word has truly been spoken. To achieve this, it uses a confidence threshold to prevent the false activations and it applies smoothing algorithm to avoid reacting to random noises or brief misclassifications. Finally, when a wake word is confirmed, the command responder takes action. This could mean tuning on a device, lightning an LED, or sending a control signal to other connected components. The responder is the visible feedback to the user, showing that the system correctly recognized the command. Okay, let's stop here. Next, we will see about walking through the test, the basic flows, audio provider and feature provider.